This is question 4 from the 2019 AP Calculus exam. So they begin by giving you this diagram of a cylinder-shaped barrel, and this barrel contains rainwater. Notice that the diameter of the barrel is 2 feet, and you can see that the height of the water in the barrel is changing with respect to time. Water is draining out through a valve at the bottom of the barrel. And they also give us the dH/dt definition, how the height of the water level is changing. -1/10 times root h, where h is measured in feet, time is in seconds. And notice they also give you the volume of a cylinder with radius r, so v equals pi r squared h. Now, letter A says to find the rate of change of the volume of the water in the barrel with respect to time. So I'm looking for dv dt, and I can find that by taking the derivative of my volume formula. Notice, though, that the radius of the water, which again takes the shape of the container, is going to be 1, half the diameter. And it's always 1. So technically, the volume of my cylinder is going to be v equals pi times 1 squared times h, because that radius is fixed. It's constant. It's going to be 1 all the time. So now I have a volume equation of simply pi times h, just like that. When the height of the water is exactly 4 feet, it says to find the rate of change of the volume. And by the way, rate of change of the volume, let's call that dv dt. It might be good to annotate your FRQs and underline, make notes, circle units, and just kind of write down quick little helpful tools to yourself, just keys to help you think about what we're trying to answer in the question. So let's find dv dt. I'll work out the rest of part A up here in the corner. If I know that volume equals pi times h, and again r is 1, so it's simply pi times h, let's take the derivative of both sides with respect to time. So dv dt is equal to pi times dh dt. This is implicit differentiation, but again with respect to time. And then it says when the height of the water is exactly 4 feet. So I'm just going to go on a little detour here to find out what dH dt is equal to when the height of the water is 4. So -1/10 times the square root of h, or square root of 4. That's going to give me a value of, looks like -1, -2/10, or -1/5. So I have a dV dt, the rate of change of volume of the water, is pi times -1/5, or a final solution, we'll call that just -pi/5. Let's put proper units on this. It's a rate of change of volume in cubic feet. So feet cubed, cubic feet per seconds. Yes, there we go. -pi/5 cubic feet per second is the rate of change of volume. Now letter B. Next part says, when the height of the water is now 3 feet, is the rate of change of the height of the water, be careful here, this question is asking us, is the rate of the height of the water changing, increasing or decreasing specifically? So this is sort of going to go after a second derivative analysis right here. How do I know if a rate is increasing or decreasing? I need to analyze its second derivative. So let's go back here to dH dt and find the derivative of dH dt. So d squared h divided by dt squared, there's the derivative of dH dt. Well, let's take a look here now. I'm going to do if that is equal to -1/10 times h to the 1/2, let's do a power rule. So I'm going to have -1/20 h to the power of -1/2, don't forget the chain rule, times dH dt. Always take the derivative, at least in this case, with respect to time. So there's my definition of the second derivative, and I'm curious about whether the rate of change is increasing or decreasing. So really all I care about is the sign, S-I-G-N, is the sign of this second derivative positive or negative? Let's do a little bit more investigating. It says when the height of the water is 3 feet. So plug in 3 for h. I have -1/20 times 3 to the -1/2, or just 1/3 to the 1/2, so 1/√3, but then times dH dt. Now, what is dH dt when the water is at a height of 3? So another detour here. dH dt is going to be negative 1/10 times root 3, or just negative root 3 over 10. Now, again, I don't really care about what this all simplifies down to. All I care about is the fact that it looks like we're going to have a positive second derivative. Negative times negative is going to be overall positive. So this is going to be greater than 0. My conclusion is that the rate of change of the height of the water is increasing. Is increasing when h equals 3 feet, comma, because, it does say to explain our reasoning, so we should say why or how we know, because the second derivative, d squared h over dt squared, when h is equal to 3, is positive. All right, so there we go. An increasing rate of change. Part C, final question right here says, at time 0, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. So we're going to solve a differential equation. Let's do that right here. We're going to solve dH dt equals negative 1/10 root h. Let me just rewrite that actually with the h's on the left. We'll separate first. So how about 1 over the square root of h times dh equals negative 1/10 dt. Push your h's on the left and then bring the t's to the right. And I'm going to further just write this as maybe some easier notation here for me to do this antiderivative. All right, h to the negative 1/2 dh equals negative 1/10 dt. I'm now ready to integrate. So separate, integrate. Let's do that right now, left and right. The antiderivative here by reverse power is going to go to 2h to the 1/2 equals negative 1/10 t plus c. We'll put the constant on the right-hand side. And let's solve for c. We know that at time 0, the height of the water is 5 feet. So using h of 0 equals 5, I'll have 2 times 5 to the 1/2 equals 0 plus c, or essentially c equals 2 root 5. I'll bring that 2 root 5 back here into the original problem, and we'll go 2h to the 1/2 equals negative 1/10 t plus c, but I now know that c is equal to 2 root 5. And at this point here, we're just trying to solve for h. So let's divide everybody by 2. H to the 1/2 is just the square root of h. Divide by 2, so negative 1/20 t plus 1 root 5. And then finally, square both sides to solve for h. So down here, h is equal to negative 1 over 20 t plus root 5 quantity squared. And that'll be my h of t. Let's write that h of t function. And there we go. So that is at time, let's see here, at time 0 seconds, the height of the water was 5 feet. We used the initial condition, and then we solved the differential equation. We actually found what's known as the particular solution to that differential equation by solving for c and then using it to isolate that dependent variable. I now have a function of h in terms of t, and that's exactly what the question asked us to do. So this FRQ talked about solving differential equations, and it also talked about using related rates and implicit differentiation to do a little bit of derivative analysis on this situation. So I hope that was helpful. As always, thanks for watching, and be sure to check out the other 2019 FRQ questions.